Um, so anything, Amit, you want to ask related to project and all things?
No, sir. I have some other question.
Okay, so you can ask any question. We will continue
Sir,
after
in
that.
formation evolution, we have miscellaneous logs.
Miscellaneous logs. Uh,
So can you please explain about it?
1 minute. Uh, is it in course of Gate?
No, sir. It is given in Petrogate Academy book.
Okay. Actually, I'm not familiar with this name. 1 minute. Just let me Google it once. Which kind of log they are covering in this,
In
or this is the
miscellaneous logs given caliper log NMR.
okay. NMR and okay, understood. NMR. So, uh, can you do one thing? I have one video on YouTube regarding to this in Get in Petroleum itself, NMR log itself and caliper log itself. Just go through that once. Any doubts you can ask me later, na? Because
Okay, sir.
NMR is itself a 1 hour or 2 hour topic. And again, if we will cover calculation of that, which might not necessary for GATE, and it's a hypothetical basis, so that will again take 1 more hour.
Okay, sir.
And you can read this NMR log. I think I have one material. I will share that in group. Let me find that because I was not doing this stuff for a longer time. So I will share that within a week. Okay. Just remind me if for I forgot. I will forget this in next Saturday. Okay.
Okay, sir.
Okay. Good. Okay. So we can continue now. So I think someone, I think Arpit has asked saturated liquid and saturated vapor. So it is required for this thermal flooding. So we are going to discuss thermal flooding from next session. So let's suppose we have a pressure and volume. What we may have, we have a pressure versus temperature. So you know this diagram. Hope this you know. ऐसे ही होता है ना थोड़ा स्ट्रेटिंग होगा ओके गुड अभी के लिए इसको कंसीडर करते हैं 2 3 थोड़ा नीचे वाला okay so we know this is solid, this is uh, gas, and this is liquid we have. And what is this point? Are you familiar with this diagram? This is pure component phase diagram.
Yes, sir.
Okay. So pure component phase diagram. So this point is a triple point where all phases are coexist. So we have a this critical point. Okay. So let's say this is a pressure versus temperature diagram, but I want to add third parameter as a volume. So let's say it's hard to visualize in 3D. So what we are doing, we are extracting pressure volume diagram for this liquid and gas. Okay. So for liquid and gas, John, this curve is something like this. And in this case, this point should be a This point is a critical point. Okay. And at a constant temperature, the curves should look like this. Okay, this, let's suppose T is equal to 200 Kelvin. Then this at a higher temperature, this is something like this. 300 Kelvin, and let's suppose this is T is equal to, then it will start to go like this. Okay. So this critical temperature is 400, then this may be a 500 Kelvin. And this point and this point. So this is liquid plus vapor zone. This is liquid zone and this is vapor zone. And this point is A. This point is B. Then this your A is let's suppose this is liquid zone. This is liquid plus vapor zone. So at this T is equal to 200 Kelvin. What is this A and what is this B? Can answer you? What does this pressure value is? What is this A and what is this B point? Like what is this A and what is this B point? Very simple, yeah.
Bubble and dew point.
Yes. So which one is bubble point?
B is bubble point. No, no, no.
A is a bubble point. Just consider what you know now this one. So this is bubble point curve. So 100% liquid. So this is liquid zone. That means here we have 100% of liquid and here we have 100% of gas. Okay. So A is a bubble point. B is a dew point. But you can observe one thing, dew point and bubble point both are equal. Okay, so pressure are equal. So whenever you have a single component, so you can observe here at constant temperature, if I want to convert any liquid to this gas, then it is a single point itself. It won't belong to at a single point you can convert. So this point is a bubble point as well as the dew point. Okay. For that particular temperature. We are talking about here T is equal to 200 Kelvin pressure. But within that pressure and temperature, its volume change in such a way that it creates a two-phase zone region. Okay, here we can't observe because we do not have an additional axis as a volume. This is the projection in PT phase, so it is simple straight line. So single bubble point pressure and dew point we have here with a constant temperature and pressure. Okay. So this is for a single component. Okay, I'm writing here for a single component. And this A is a nothing. You can say A, whatever we have A. Let's suppose A is the point. It's a saturated liquid. That means 100% liquid. And B is a saturated vapor. C is a, let's suppose if this is zone C and this is zone D. So C is a superheated vapor. Sorry. And D is a, okay, it's a below, beyond this, that point. So we can't say it's a D. We are not going to in that solid zone because it's we are not going to cover that solid matter or anything here. So you have to just think regarding to this only. So are you able to understand this curve? Let me clean up because not I would not like to use that same curve. Mm, Let's say let's say if this is my curve and let's consider at particular temperature. So this is pressure, this is volume, and this is temperature is equal to 200 Kelvin. So what's happening here? While we are reducing the pressure at a constant temperature, let's suppose this is A zone, this is B, and this is C, then I can say in A, uh, temperature we are reducing and no phase change occur. Sorry, pressure we are reducing and no phase change occur. Any phase change are you observing in A zone? No, this is liquid plus vapor, this is liquid and this is vapor. Okay, this is C. So no phase change. In B zone, what's happening? Uh, let's say what we are doing, we are pressure is a constant and we are changing the phase. Okay, and in C, pressure we are changing or we can say reducing and again no phase change. Okay, so these three observation we can observe. Let's suppose consider another temperature line. And this is very important for because it can directly ask this kind of question. This is 12 standard question again. This is at a temperature, let's suppose 300 Kelvin. This is at a 200 Kelvin. Let's suppose now consider this point as a, let's say A dash. Then this will come to this. Don't use ABC here. 1, 2, 3 we can use in place of that in Roman. So let's suppose this is point 1. This is point 2. Let's suppose it's moving toward this and we are reaching here. Okay, at a constant pressure. Now we have a pressure as a constant value. Let's suppose 3 atm. Okay, and let's suppose this is 2, this is 3, and this is 4. We are moving this side. So what I want to do, let me tell you. So what I want to do, my pressure is a constant. Okay, by changing temperature from 1 to 4, I want to change a phase. Okay, what my goal is, I want to change phase for this particular, let's suppose it's a pure component. So let's suppose methane and whatever you want. And what I want to do, so I want to change the uh, my temperature value and I want to change my phase. Okay, I can keep constant any one parameter. So I want to keep pressure constant. I want to change temperature from 1 to 4 and I want to change the phase. So definitely volume will adjust according to temperature changes. I can't keep those two parameter constant because in that case we observe that thing na its degree of freedom will its degree of freedom becomes 0. That means its system is defined. You can't change anything. So I can keep any single parameter constant. So now degree of freedom is 1. Okay, we understood that. So if I will fix temperature, then I can fix the volume itself. Okay, at that definite volume we will observe. So here let's say we are moving from 1 to 4. So what are the activities we are observing at a constant pressure that we are going to understand. So at a 1, let's say at a 1 we are at temperature is equal to 200 Kelvin and at a 4 we are at a temperature of the 300 Kelvin. Okay. In between, how what are the points we are observing? 2 and 3. Okay, so we are moving from 1 to 2, then 2 to 3, and 3 to 4. And what our observation are here? Uh, in zone 1, can I say we are changing the temperature, but not changing the phase? Because definitely again here we have a other line, because I have not drawn all lines. Let's say we have another line here. Okay, definitely we have that line. We must have a line here. Okay, this may be temperature is equal to 250. Okay, so in zone 1 we are reducing the temperature without changing phase. Okay, in second one, what we are doing here, we are changing the phase, because we are changing liquid to vapor. And you know, at any particular point I can calculate percentage of liquid versus vapor. So let's say I want to calculate percentages of liquid at this point, then what I will consider, this is the my height divided by this entire height. Okay, like for this and this, then if let's say this is A, this is B, then B divided by A plus B will give me the liquid fraction, because we know inverse rule we can follow from 100%. Okay, that we know. So that you know. So what activity we are observing here in B zone? Okay, so in B we have a we are not changing we are not temperature is a constant, but what we are doing, we are changing we are changing the phase. Okay, and in third, again what we are doing, we are now in a complete vapor zone. So here in this fourth zone, in this line, we are not changing the phase. What we are not doing, we are not changing the phase, but we are increasing the temperature or decreasing. Okay, we are increasing the temperature. Okay, definitely we are going liquid to that side, so definitely we are increasing the temperature. Okay, again what we are doing, without change in phase. Okay, without change in phase. So these are the observation. So now whatever heat associated with these three taps. Okay, so we know this heat and this heat. So this heat known as the latent heat. Okay, then this heat is known as sensitive heat. This is again sensitive heat. And you know, while we are changing the temperature, total energy required is equal to mc delta T. Okay, m is the mass, C is the latent, or you can say sensitive heat value, and delta is the temperature difference. Okay, whatever temperature difference we have. Similar here we can write Q is equal to mc delta T. And for this case, what we can write, Q is equal to m lambda. So this lambda is a latent heat. Okay, so remember these things. Now you can do any calculation. Just draw a diagram, small diagram, and just calculate what you are want, where from where point to. You can now move from any single point to other point. For an example, let's suppose if you are here and I will tell you reach here, then what you will do? Either you can go this, and then you can reach to this. Okay. So here again you can see temperature difference. Here again you can see pressure difference as well as temperature difference. So we are not going to discuss how can we calculate for pressure. It must be P del V. Okay, simple. P or you can say P del V plus V del P, something like that. Don't want to discuss that thermodynamic. Or what you can do, you can just follow straight path. But consider for a now straight path. Okay, so you can change from any point to from this liquid zone to vapor zone, and you are able to calculate the heat values. Okay, you can calculate this Q value by keeping this is delta 1, that is delta 1, this is Q3, this is Q1, and this is Q2. So you can just write unit for lambda and for C. So you can see this is let's say if this is in joule, then this should be joule per kg into Kelvin, and this must be joule per kg. So unit will adjust accordingly, and this can be asked in your final year viva or in your intensive viva if Negi sir is present. Okay, so just remember this all thing. What is sensitive heat, latent heat, heat of combustion? These all things you should remember, and you should focus on this. At least you can solve one 12th standard problem by this. Okay, so any doubt in this, or it's clearly explained to you? Because basis of this you may get question in thermal flooding, so I want to explain this. Hello,
Yes, sir.
any question?
No, sir.
Okay, are you able to understand this? Because this may be helpful in reservoir also in production. तो ये तो बहुत काम की चीज है हीट एक्सचेंजर डिजाइन में और उसमें.
Yes, sir.
So you can go from any single point towards the horizontal line of any other point easily, na?
Yes.
Okay, so this is from my side for visible flooding, and we have already started thermal flooding as well. Uh, so any doubts or anything you want to ask, or we can conclude this session for today.
Hello, sir.
Yes,
How long it will take, sir, now onward?
for EOR,
For this lecture, sir.
uh, let's say still we have covered flooding part. So within next two lecture we are going to cover thermal flooding. Then in next lecture we are going to cover chemical flooding. Chemical flooding won't take too much time. Then in next so three lecture for this theoretical part. Then regarding to calculations and all important things, it will take two lecture more. So maximum six lecture you can say, or I will try to cover in five lecture also. But six lecture from my side is required for me to explain concept thoroughly. Okay.
And sir, for today's lecture, it's over, na?
Yeah, for today you can stop recording.
Okay, sir.
So I will